So everything we learned so far is embarrassing. I mean, just stuff we should have known in grade school. And Dr. Sherbakov's, he went to some amazing middle school where, you know, they knew everything already. It was in Kharkiv, and today it's a ruin thanks to the Russian fascists. But they taught him all this already then, apparently. At least that's what he says. So now, this is a little bit more complicated. Can we get something more out of this? So now the question is, what is a symmetry? The basic idea of symmetry is that I do something to my law, and the law doesn't change its form. So, you know, this is a function of many, many variables, but it's just a number. And if I change the variables in a way that respects the symmetry of this number then doesn't change. So that's called invariance under symmetry transformation. If you do it for things like Dyson-Schwinger equation, then what happens at every lattice site, this is counting lattice size. This has to be satisfied every place, so it's a vector. So then the symmetry is something says that the law doesn't change shape even though coordinates have changed. So applied mathematicians call this equivariance. Physicists don't get what's the big deal, so we call it invariance. I mean, you know, so yes, if I take the derivative, then, you know, it changes according to the symmetry. What's the big deal? But mathematicians are slow, so they have to keep distinction. It's really not necessary. So now the symmetry is the following thing. If I have the law, and I change it a little bit, the law itself doesn't change, which means that this guy has to be 0. So continuous symmetry is if you deform your coordinates a little bit in such a way that, for example, distances are preserved, so you're turning some radius or something, then you get a relation on the level of the law. The classical relation is that you have a little change of your law along coordinate I. So, you know, the picture you have is, so you have a change, which is this guy phi of your position. You know, this is your position in a space. This is the origin. And let's say this is a distance, or whatever you want to have preserved. And to make the distance preserved, you have to make sure that you're moving in orthogonal direction to it, infinitesimally. In other words, that my deformation locally at that point is such that I'm not changing the value of the action. Action is invariant. So this is classical symmetry. Yes, I have to make sure that I don't get the trace term. So, you know, in examples of like rotations, etc., we will check that that's true. But you're absolutely correct. This term, well, it's doing the right thing. So I think I'm okay. It's satisfied automatically. What's the quantum version of this? Well, you know what this thing is? That's called the first derivative. Well, okay, I'll just write it down. You can chew on it later. Acting on partition function equals 0. So remember, that just came from this equality, and we are keeping So this is classical, and this is quantum. Now this J can be anything, right? So forget it. So I told you, everything that has somebody's name was invented by somebody else. All the good ideas are very simple, and they have, for some reason, people like to give them names. So this thing is called word identity. Now I like this particular naming because Ward was a very intelligent but independent spirit. So he was a sailor. He went to work on the transatlantic and oceanic ships as a sailor, carrying stuff around. And when he was, at Oxford, Cambridge, someplace, he derived the identities, these identities, quantum electrodynamics, and it turns they're very important to make sure that your calculations are correct. They take care of what happens in quantum electrodynamics is when you integrate this, there are things that are called fibers. They're like spaghetti. They're part of the integration which goes from minus to plus infinity in this infinite space where the action doesn't change. This is very bad because you multiply your integral by infinities, but they're boring infinities. Nothing happens to it. So what you do is you take a knife, you look at your bunch of spaghetti, you cut them. That's called base manifold. And you just evaluate everything. And the way you cut them, the French do it different than Italians, etc. That's called gauge fixing, gauge choice. And to make sure that everything is correct, no matter how you cut it, you have to use word identities. So they're very, very important. We'll use them. But for once, the guy who wrote the thing that was known since, it's not actually quite sure because lots of our understanding of geometry is from the 20th century. I mean, it starts with Lobachevsky and Minkowski, etc. in 19. But so maybe, this is already only 20, 30 years before he did it for physics. But anyway, they're important. And they're nothing. They're just things that says if when I change coordinates, I have to make sure that if I'm changing my coordinates in a way that is a symmetry of my classical law, the quantum law, the thing that has all the quantum corrections, has to make sure that it observes this relation. So this is a quartal version of the symmetry. So here we are. If you go to any reputable course, it doesn't look like this. It says that this deformation doesn't change the action. On infinitesimal level, there is a little epsilon here. So it says, if I change my coordinates, like I rotate my fields that action is defined in, because I'm in Euclidean space or something, rotation is something that has to be orthogonal to my invariants. Like if you have a distance as invariant, phi should be something that's 90 degrees at it. That's what this means. This one is the, I have to make sure, as you pointed out, that volume is conserved. This has to do with conservation of the volume when I do this transformation, right? That one came from volume conservation of the coordinates. So, I have to make sure this works. And there are very famous things in quantum physics where people forgot this term and wrote whole theories about it, and experimentalists found the phenomenon, etc. Eventually it just goes away because somebody says, but you forgot the Jacobian. In particle physics, people have forgotten to check this term, and it costs you lots of money. Well, by that time they're tenured, so you can't do anything to them, but you never listen to them again. If they have forgotten Jacobian, sorry, I don't want to read your next paper. Life is too short for elementary errors like that.